Okay, here we go. So, what did we get? Yeah. Is this, okay, what did we get over here?
0.
Oh, 0 is right.
1.
Good.
Oh.
0. Okay, so I tried to trick you. You're too smart for me. This didn't end up being 0 over 0, right? This is one where it's an easy one.
How do you know that?
How do we know that? Because when I'm taking the limit as theta approaches pi, right? So what I'm really doing here is by using direct substitution or direct evaluation, I'm just plugging pi in every place and evaluating that expression. So I'm going to get, if I do this, I'm just going to get cosine pi times tangent of pi times
over pi.
Oh, but you know what? We actually do have a problem there, don't we?
Yeah.
Ooh, we have a problem.
What's the problem?
Ooh, the problem is, you tell me.
Too much pi.
Too much pi. You might say that, yeah.
No, what is the problem?
Tangent of pi tangent of pi is
0 over -1. How do we know that? It's 0 over -1. Because we were in precalculus.
cosine, actually cosine of, isn't cosine of pi?
Cosine
Oh, that's right, negative 1, never mind, you're right, yeah.
-1
Thinking of pi over half. That's good, that's good.
1, 0.
So we end up with -1 times 0 divided by pi. So we get 0 over pi, which is just 0. We're done. Good. Okay. Question?
How did you get the -1 to 0 again?
Because I'm just evaluating what is the cosine of pi. If I look on the unit circle, right? Remember on the unit circle, if we've got some angle, then the coordinates on the unit circle, let's call these coordinates x and y. What does x represent?
Sine.
Cosine. Y represents sine. Okay, an easy way to remember that is, alphabetical. C before S, X before Y. Jennifer, question.
So for the cosine and the tangent, like, could you simplify that to just sine?
Sine, yes, sine over cos. Yeah, you could. Absolutely, you could. Sure, because you know that cosine is tangent is we could replace with sine pi over cosine pi, right? And then the cosines would cancel. Yeah, you just make it sine. Very good. Good job. Okay.
So let's try this again.
Okay.
That makes sense.
Either way, I mean, that you certainly could. Either way, though, the tangent is sine over cosine, right? And so if we're over at pi, we're right here, aren't we? So my coordinates are going to be -1, 0. So the cosine is -1, sine is 0. Right? Make sense?
Yes,
Okay.
that makes way more sense.
Okay, so moving on.
I just. Okay, so then you get 0 divided by pi, so that's just 0.
That's just plain old
So
0.
that's how we got it. Okay.
That's right. Okay, but now I'm gonna. Oh, I didn't like that. What am I doing? Oh, come on. Okay, let's make a little change-a-roo. Yeah.
Now.
Now what?
Okay.
Yikes. Good idea. What's that? Yeah, it is 1.
That's what I
You're
did
right.
the first time.
It's 1. And this, now here's where Jennifer's little hint proves really helpful, doesn't it? Let's remind ourselves though, why are we doing this, right? We're talking about taking limits analytically. The only kind that really requires any attention by us at this point are those nasty 0 over 0 ones, right? The no limit ones. The rest of them are easy. We just evaluate them. But so what's going to, as theta approaches 0, we're going to have a problem because, well, what's the cosine of, what's the tangent of 0? Tangent is, it would be sine over cosine.
So it's 0.
So it's 0, isn't it, right? So on the top, would everybody agree, it doesn't even matter what cosine is because we know that the tangent of 0 is 0. So the top goes to 0, bottom goes to 0, more work, right? It's indeterminate. Okay, so we've got to somehow eliminate that indeterminacy. Sometimes, sometimes you're going to be able to just manipulate trig functions using identities so that you can cancel factors, but not here. I mean, you could, but it's really, really difficult. Instead, we're going to rely on those special, it's been a while, but those two special trig identities that we developed prior to Roundup. Can you remember? Say it again. The limit of sine theta over theta as theta approaches 0 equals 1. That's the heavy hitter. That's the one you use most of the time. The other one you can derive from that, but it's probably just good to know. The other one is limit of what? Remember?
Tangent.
No.
Oh, 1 minus cosine theta over
Yes,
theta
I wrote this down.
Equals 0. Yes. Okay? Those are our two that we just are going to remember. I don't like people to remember very much at all, but those are two that you just have to kind of remember. We don't want to waste brain cells remembering facts. We want to save them for processes, but those are a couple you got to know. So we want to exploit these. We want to somehow algebraically manipulate. Now, does it make sense to you? I want to make sure, I want you to start being able to talk like mathematicians. When I talk about the argument of a limit, do you know what that means?
People aren't
Okay. Whenever in math, whenever you talk about the argument of something, it means what's inside it. So if I talk about the argument of the limit, I'm talking about that. It's the limit of what? Its argument. Okay? So we want to algebraically manipulate the argument of the limit so that we can force one of these special forms to pop out. And then we know those answers, and so that will remove the indeterminacy, right?
Okay.
So how are we going to do that? Yes, yeah, sine over cosine. That was Jennifer's trick, right? So we're going to just do this, right? And that's a good general strategy. Remember, we always, when we're trying to do any kind of trig algebra, it's a great idea to write the compound trig functions in terms of sines and cosines, and then lots of stuff happens, right? We have lots of trig identities for sines and cosines. A lot of times we get cancellation. So this just becomes limit of then cosine theta times sine theta over cosine theta all over theta. And look at the cancellation, right? The cosines cancel vertically to 1. And now I can evaluate my limit, because what I'm left with is just this guy, right? So the answer is 1. Okay, good? Okay.
So would it be 0 if we left it at cosine? Since we changed it to cosine over.
No. No, okay, good question. The question is, would it have been 0 if we left it as cosine tangent? No, we didn't change anything. All we did was we rewrote, right? We can't change the answer. The answer is the answer, right? We're just going to try to use algebra to reorganize the argument so that we can make it look more recognizable, okay? We didn't change anything. We just found a way to get to the answer. Yes, Clancy?
So cosine was the factor that was making it like hidden or whatever?
Yes. Yep, so cosine was the factor, yeah. Well, you know what? Let me say that again. That's a great question, because we've always had that, haven't we? In the past, we've always had, when we're dealing with algebraic indeterminate forms, we've always had some factor cancel. Actually, no, that's not the answer, because cosine, think about this, cosine of 0 is 1, right? So all we did was just cancel some 1s. This is kind of a disguised one. Where does the indeterminacy come from? Remember that proof we did, that geometric proof? That's where it comes from. And so it's just, if we can get it to look like this, that's an indeterminate form. But we've already proved that, not by canceling factors, but we've already proved in another way that this limit is always equal to 1. So whenever we encounter that limit, we always know what it's equal to. So that's how does that make sense?
Mm-hmm.
Okay. All right, let's try another one of these. One more of these, how about? Okay, let's see. A good one would be this guy. That's a good one. Oh. What's that one? As x approaches 0. What sign 0?
Wait, isn't it no limit? Because you have a number over 0.
We do?
If we plug in 0, don't you? Because tan will equal 0, and then 1 minus 0 is 1. So then what? Yeah, what if you cosine of 0?
Yeah, right. Okay, so let's look at this limit here. If we evaluate the limit, would you agree that the sine of 0 goes to 0, right? The cosine of 0 goes to 1. The tangent of 0 goes to 0. So we get 1 divided by -1, which is -1, done, right? Okay. Okay, I'm gonna throw a really tricky one at you. Yeah.
I tried to like break it down, like separate it. Can you just do that? So I know what I did wrong.
Well, okay, yeah, we can, and we're gonna do something like that in a second because I'm gonna change this up. But you don't want to. You don't want to if you don't have to, right? Because it's much easier to evaluate than it is to simplify. And so what you always want to try first is you want to try direct evaluation. And I know we're a little rusty with our trig functions, but that'll only last for a few days, and then you'll instantly remember what all the trig functions are. I might even help you with that. Maybe we'll do a little trig identity quiz or something to force you to remember them, because I think that would be a bad idea. Just at least just the important ones, not a lot, but just to know what I would like you to know. I would like you to know. Well, I'm not going to bog us down with it right now. I will let you know on Thursday. We'll do a very brief review of just kind of a tour of the unit circle. What are the important points and the things that I want you to know? And you tell me if you think I ought to maybe do a little quick quiz at some point to help you remember those, because you really do need to remember them. But my point is just that I got off track. Janelle, you first want to just try to evaluate to see if you have a problem. I mean, if we don't really have to do any algebra here unless we end up with a 0 over 0, right? And then we're going to have to do some stuff, right? But if I can just evaluate all these pieces and that doesn't happen, I'm done, right? Okay, but let's change this so something does happen that causes problems. Okay, so instead of approaching 0, I'm going to really throw a curve at you. We're going to approach pi fourths.
Oh, that's when you got to use our triangles.
Or this thing.
Well, maybe. Yeah, so you're going to want to use your unit circle, right? Let's throw a unit circle up here. Okay, where's pi fourths? Okay, so that I interpret that as right there, right? Okay, that's pi fourths. Pi fourths, what are the coordinates?
Pi square root 2 over 2.
And?
Negative
No.
1. Square root 2 over 2.
Because we're in quadrant 1, right? Okay. So now that seems kind of bad, right?
Yeah, but how does that have anything to do with pi over 4. Sorry.
Oh, because
Oh, it's a triangle. I got you.
right. Okay. Okay. Make sense? Maybe we better just let's do okay. We'll do just the predecessor of our review. I want to remind you about one thing because it sounds like maybe we're rusty. It's been all summer, all around it. On the unit circle, what are the only numbers that appear on the special points? And we know the special points are just here, 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 there, right? And then all the translations of those, right, around the. So there's lots of special points, but they're all really just copies of each other, right? You know, and one of the things I would claim on the unit circle is, if you know unit 1 or quadrant 1 really well, then you know the rest of the unit circle, right? The rest of it is really easy to populate if you know quadrant 1, okay? What are the only numbers that show up in the coordinates of the special points?
Pi over 6, pi over 3, pi over 4.
Okay, so those are the angles. Those are the angles. We're going to get pi over 6, pi over 4, pi over 3, etc., right?
45, there's a pi over 6.
Okay, but no, what I'm looking for here are these kinds of numbers. I want to know what are the coordinates of the points on the unit circle.
Those are what
1, 0.
Okay, and let's do this. Let's write them down first, and then I want to put them in order. So we obviously have 0, 1.
Wait. What? Wait. 3
Square root of 3 over 2.
2.
Obviously, we have square root of 2 over 2, and
1 over 3. 1/2.
1/2. Okay, make sense? We all remember those, right? Those are ringing a bell? Okay, let's put those in order. Let's put those in order from smallest to biggest. So in order, 0, what? 1/2, right? Because isn't this, I mean, these have all the same denominator. Square root of 2 is bigger than 1, right? Next.
Square root 2 over 2. Square root 3 over 2. 1.
Okay, so look how this goes. It's really simple. If you know quadrant 1, and we'll talk more about this later, but we can just propagate this all the way around. If we take this point right here, this is the x-axis, right? And that's the y-axis. So think what we're doing. We're starting with all the coordinate weight shifted to the x, because the coordinates here are just 1, 0, right? As we move up towards the end of quadrant 1, the boundary, when we get up to this top point, we've shifted all the weight to the y-coordinate away from the x-coordinate. And so up here we've got 0, it's pi over 2, and the 0, 1, right? So in between, we're just going to gradually step through that process, right? So here we want to step from big X, small y, to big but slightly smaller x, to slightly bigger y, right? So where we're going to go here? So this is going to step down from 1 to square root of 3 over 2. This steps up from 0 to 1/2, right? Okay. So this one, does that make sense? So this one's at square root of 3 over 2, 1/2. Now step down, step up. So they both step to the middle, right? Now we're just going to flip-flop, right? So here we're at 1/2 square root of 3 over 2, and there we're at 0, 1, right? And then we'll just get, if we're going to quadrant 2, obviously now the x's are just going to get larger and negative as the y's get smaller, right? Down here, x's get, they're going to get smaller and negative as the y's get bigger and negative, right? You get the idea. Same numbers though, right? Just the signs changed. All we know is quadrant 1, x and y are both positive. Quadrant 2, what?
X is negative.
X is negative, y is positive. Both negative. Positive, negative. X positive and y is negative, right? So you get the idea? Okay, so at pi fourths, now the only other part of this is you've just got to figure out where those increments of fractions of 2 pi fall, right? That's easy too, right? You know that this is 0, that one's pi halves, right? Half of pi halves is pi fourths, right? So that's pi sixths and that's pi thirds. Agreed? This is pi halves, so now I'm going to step over another, I must be having to step up another pi thirds, right?
Yeah.
Or hold it, pi sixths, sorry. Right, because I'm going to move up that far. Pi sixths in addition to my pi halves that I already had. The easier way to do it though is this. Let's work backwards. If this is pi, and that's 0, and that's pi 6, then isn't this pi minus pi 6?
Yes.
Right?
5 pi over
Okay.
6.
So 5 pi over 6. And then if this is pi fourths, then that obviously must be pi minus pi fourths, so 3/4 pi. If that's pi thirds, then this is pi minus pi over 3, 1/3 pi. So 2/3 pi. You get the idea?
Yes.
Okay. So pi fourths then, right there, right? So sine and cosine are equal there, aren't they? They're both, and so it doesn't even matter what they're square root of 2 over 2, but they're going to cancel to 0, aren't they? So I'm getting 0 on the bottom. Tangent is sine over cosine. If sine and cosine have the same value, that's just 1, right? So I get 0 over 0. Okay, good. Now this takes a little analysis though. What's the problem with this whole situation here based on what I've given you? Yeah, none of these limits are going to help us, are they? We could make them help us by doing a phase shift, but that's hard. We don't want to do that. So what's got to happen here then? Clancy, what's got to happen here?
Well, it's not the factors, we've got to cancel this stuff out.
We've got to be able to cancel, and we actually do have to be able to cancel factors this time. We have to be able to cancel factors that are causing this thing to go to 0 over 0. Okay? Because we don't have access to one of these, so that's the only show in town now. Okay. So what do we do? Suggestions? Suggestion? Oh, I thought you had one. Yeah, this same idea you had earlier.
We split the tail?
Yeah.
Okay.
Could you maybe like combine the dummy and
Okay, yeah. And where that comes from, remember, is we're going to rewrite the tangent as sine over cosine. Okay.
And then with the sine over cosine, do you use like the same coordinates from the unit circle?
Say it again.
Coordinates. Would you use like for the sine over cosine? Would you use the same like coordinates from the unit circle?
Okay, but we already know we don't have to keep trying that because until we cancel something, we know that we're stuck with 0 over 0, right? Until we either could cancel something or use these, but those are off limits because x isn't approaching 0, right? Okay. So now what?
you can do 1 over.
Okay. And the way, you're right. The way that we would have talked about this, say in Algebra 2, would have been whenever we have a ratio of fractions, we always do the same thing, right? We're always going to simplify the top into one big fraction, bottom into one big fraction, flip and multiply, right? And maybe we'll look at that in a slightly different way now that we're much more sophisticated. But it's basically that's what we're doing. So on the top, I got to get a common denominator. What am I multiplying by here? Cosine over cosine. So I get limit of cosine x minus sine x over cosine x, all divided by sine x minus cosine x. Okay? Right?
Oh yeah.
Wait, but if you multiply by. Oh, okay.
Okay? So then we can, what can we do here? Well, we could, good, we could put a bunch of, these are all going to get us to the same place, but we would have always in the past said, okay, we'll just put this over 1 and flip and multiply. That's fine. That works. Or, conversely, we could also just multiply top and bottom by cosine x to cancel the cosine x on the top and get a cosine x on the bottom. Agreed?
No, I don't know what this said.
You don't know? Okay, say that again. So if I multiply both top and bottom
Okay.
by cosine x, those would cancel, and there's my cosine x on the bottom, right?
Okay.
Does that make sense? It's all the same thing, isn't it?
Let's do that.
Right? So either way we do it, whether we flip and multiply by the bottom, and I'm going to go back, that's the one we're most used to, so I'll do that.
Yeah, thank you.
So if I flip and multiply by the bottom, would everybody agree that on the bottom I'm just going to get the product of cosine x times sine x minus quantity cosine, or sine x minus cosine x?
Yeah.
Okay.
Oh, you don't.
Right. So all I did was I just stuck this up here and flip and multiply, right?
Wait, so the sine x would cancel? It wouldn't cancel anything? No, they can't. But there's a wrong way. One's positive and one's negative.
Okay, that's right. But what do we do about that?
Times
Good. Well, we were going to factor out a -1. Very good. Okay, don't tension up here. Don't lose track. Don't lose track. So then we're going to factor out a -1, and we get
On the top or
limit top, let's say. Just because wouldn't it be better to have the negative on top? Doesn't really matter. So we get minus the quantity what on the top?
Cosine x. Negative cosine.
Okay, which we could also write as
Sine x minus
okay.
cosine.
And now on the bottom we've got cosine x times sine x minus cosine x, and look what happens. There's our indeterminacy, right? Because isn't the sine x minus cosine x what caused the 0?
Yep.
Aha, right? So now those go away, and now we can take our limit as x approaches pi over 4. What do we get? Well, the top is just -1, right? On the bottom we get cosine of pi fourths, which is square root of 2 over 2. And so our answer is just -1 divided by the square root of 2 over 2. And that just -2, whoops, wow, what was that? 2 divided by the square root of 2, which is what?
A number.
Number, what number? Yeah, negative square root of 2, right?
What?
Isn't 2 divided by the square root of 2 just the square root of 2?
Sure.
What's the square root of 2 times the square root of 2? 2, right?
Wait, oh my goodness.
Yeah, let's sure? Yes, I can.
You can't skip.
Okay, so here's the question, right?
Okay.
So 2 divided by the square root of 2, think about it as a bunch of ways we could do this. I want you to just see this though, just in its own form. 2 divided by the square root of 2 has to equal the square root of 2 because the square root of 2 times the square root of 2 is 2. Okay? Now there's a bunch of ways you could look at that, and it's completely consistent, and it's great to see them both. You could look at that also as being -2 to the 1 over 2 to the 1/2, right? Right? Isn't a square root just a 1/2 power?
Yeah.
So by our sign rules, if we divide like bases, we just subtract exponents, right? Okay? So that's equal to -2 to the 1/2, which is that.
Okay, just a quick question back, I'm sorry, but back up where we canceled. If we factored out a -1, wouldn't it now be sine x plus cosine x because we took out?
No, if I factor it out, I have to undistribute it or divide it away from each term, right?
Okay.
So cosine x divided by -1 is negative cosine x, right? Okay. Did this part make sense? If you follow these sign rules, one more time. I mean the exponent rules. Okay, this is good. If you think of the square root of 2 as being 2 to the 1/2, then look, I have a quotient of like bases. Don't we know? Real quick, we'll get back to that. Don't we know that if we have a to the m divided by a to the n, isn't that equal to a to the m minus n?
Oh, yeah.
Right? Okay, well, a to the m, a to the n, a to the 1 minus 1/2 is 1/2.
Or if we didn't keep it, if we kept it 1 over square root of 2. Then it'd be
Well, okay, yeah,
But
1
where
over
does the
square root of
big-
2.
No. Where does the big 2 go?
Well, no, it can't because, see, the problem is, okay, too much talking, I'm getting kind of distracted. Everybody look up here, please. See, the problem is, it's not, we had a square root of 2 over 2 on the bottom. Technically, we don't want an irrational number on the bottom. So when we flip and multiply, we've got a 2 divided by the square root of 2. right?
Still wrong.
Which is still,
1 over square root
But
of
then
2.
you multiply it.
right, okay, and then the other thing, right, so the third way you could do this, and I'm sure people are just saying in their minds, why is he going? Because this is what makes you a good mathematician. If you can see how all these common threads kind of wind together, that's when things really start to click. So the other way we could do this is just by the traditional rationalizing the denominator. What if we multiply by square root of 2 over square root of 2? Wouldn't I just get 2 square root of 2 over 2? 2's cancel, right?
Yeah, that makes more sense.
Well, they all work, but I think it is important. I mean, and it's not like you have to come away with this being an X, but every time we go through this, I promise you, and the metacognitive research that underlies it, it's so fascinating. But one of the things it says, and this is really important to know about your brain, when you're learning something like math that's highly analytical, there is a ton of that your brain is working out tremendously. It makes you smarter in all areas because it increases the interconnectedness of the neurons in your brain. What makes you smarter is not the number of neurons you have. The number of neurons you have is highest when you're just a kid. And then you bump your head and you lose some. You know, they go away your whole life. So you're losing those. But what makes you smarter is not the number of neurons, it's the interconnectedness of the neurons, right?
Oh, so
It's the degree to which the dendrites and axons connect the two.
so is that why we need to learn things that we don't usually learn?
Well, it is. It is. Like, for example, Einstein's brain was finely cross-sectioned to study why he was so darn smart. His brain was average size, completely average size. But he had this, I mean, it was heavy because he had all this extra dendritic connective tissue in there that connected these neurons. And when you increase, you got to kind of think of it this way a little bit. Imagine, this is interesting, so I'm going to take a second to talk about this. Imagine that everybody in here just takes a piece of rope and just connects it to one other person. How many connections are there? Well, not that many, right? I mean, there's as many connections as there are people divided by 2, right? Not very many. Now, what if you connect that piece of rope to 2 other people? Okay, now things start to get a little crazy. Now you start to get a higher degree of interconnectedness. If you took a rope in here and you connected it to 10 other people, everybody did that, you know how many connections you'd have? A lot. We're not gonna, I mean, it would be just staggering amount of connections, right? And so when you develop this interconnectedness in your brain, it's kind of an exponential process. If you can build these physical structures in your brain, you can use them for everything, right? And so that's how you get really smart. That's why was Einstein so smart? Well, probably genetic a little bit, but also, what did he do all the time?
Math.
He just thought. Yeah, he did math. I mean, he just thought about stuff, high-level stuff, all the time. He was always doing puzzles of some kind, and that's what makes you smarter. You really do. You get, and there's some dorky ways you can get a lot smarter for free. I mean, they're going to laugh at some of these. Athletics is great because the connections you make for precision movement, that adds to the complexity. If you do things, and this is a crazy one, but if you do things like try to occasionally, when you're eating dinner, just eat with your offhand. If you're right-handed, eat with your left hand. That does a lot because if you're right-handed, for example, you have a really intricate structure of neural pathways that control all the fine motor movement. Because with your right hand, think of the things you can do. You can write finely. You can't do that with your left hand, though, right? Try to do that with your left hand. It looks crazy. So if you practice making finesse movements with your weak hand, it really does. It helps. There's research shows that helps. Things like learning math is about one of the very best things you can do. Learning math and doing puzzles, kind of logic puzzles, all that stuff helps. Learning a language helps. But doing academic stuff, it really does give you something that's going to enhance your ability to tackle the world for the rest of your life. And so math is the most powerful contributor to that whole process. So do math. Math is good. It's also really important, and this also, I don't probably have time to talk about this a lot today. It's really important that your brain goes through a sleep period of a certain duration if you want to internalize the things that you learn. Did we talk about this?
No, we did, but we probably won't do it.
It's got to be. I'll have to go relook at that research, but I think it's supposed to be like 7 hours. Yeah, which is a problem with the high school schedule, but to the degree you can, that really is important to do. You're better off, honestly, I'm a teacher telling you this, you were better off at some point just not staying up late and studying for a bunch of stuff, like you're studying for a test. It doesn't work. It really doesn't work. And there have been research studies that show, for example, a person's ability to learn to do something simple like hit a ping pong ball or something. If a person comes in and does this, okay, if you get two people, equal situations, they go learn some new motor skill. One of them goes home, gets a good night's sleep. One of them, it doesn't get enough sleep, gets less than that threshold by a certain amount. They go back the next day. There is a huge difference between the retained capacity to perform that motor skill. And so there really is, there's a strong motivation. I mean, if you want to succeed in school, it really is important to build into your schedule an opportunity to get enough rest, which is hard to do, but sometimes that might mean making some tough choices, but it really is critical. I think it's something that everybody should know about. Okay, back to business. Yeah, all right. So, when are we out of here? Oh, all right, well. Okay. Wish I could remember all that stuff, because we only have a couple minutes. All that stuff about the sleep study, that was really interesting. I think the idea was, no, you know what, there's, honestly, and I don't disagree with that. The most academically successful country in the world by far is Finland. And in Finland, there is almost no homework. Students get almost no homework. The days are slightly longer, but there's a lot of time. Students study fewer topics at one time, but like you'd probably have like 3 or 4 topics that you're studying intensely. But the time that's spent would be more like what we do in the lab. Like there's time where you're intensely going through stuff under the purview of teachers that know how to help you out when you have questions. But then you're strongly encouraged to kind of put that away because it really does help. They actually, in Finland, they have high school recess where people get a significant, like for every 2 hours you spend in class, you have to have, not including passing periods, you have to have a minimum of a half an hour of absolutely free downtime. So you can just unwind and be social, and that helps. It helps people prepare to learn. So. What's the question?
Give it 2 hours left.
Yeah, no, it is. You're right, and that's why colleges work better. Yeah. No, not at all.
Like if I wanted to make it straight. Like for us, because it's hard. So maybe like
You can.
It's not that hard.
No, it's not. It's not as
I
hard.
feel like it's like just basic math.
This is really important. It's totally different. It's really, I love it. It's really not and it's really important. We don't. It's too bad that we don't do more of it. So that's.
Yeah, it's actually so.
What do you?
Actually, writing
Oh yeah. I mean, that's fine. I mean, you're gonna do calculus in college.
Yeah, I have to. So I want to get like out of the way.
I think it's, yeah, I mean, everyone's gonna do some more of this in college. Are you talking about doing it like in lieu of this or in addition to, or in addition to? Good. Awesome. All right, yeah. You want a PhD? Yeah. That's what. You might change. You should. Don't close any doors yet. You would be something you might. I've got two of my really good friends. One of my very best friends is the Western Hemisphere head of marketing for and he started off with a lot of work with like he didn't have that. He just had a Sure. Okay, yeah.